Okay, so today we're going to be doing another LeetCode challenge. We're going to be doing 5 questions, just like last time, and these questions are going to be varying difficulty, increasing as we get further along. And last time we did string-based questions, and this time we're going to do some array questions. And once again, there is no shortage of variety in these, in terms of the algorithms in these questions. So even though they're all array-based, we're going to be using a variety of different algorithms. So as I attempt these problems, I'm going to try to explain my thought process and how I would approach these problems and try to implement the solution on the spot. It may not work the first time, and that's fine. That's part of the experience. And if it doesn't work, then we're going to go through the debugging process together. Okay, so without further ado, let's get started. So the first question is called number of good pairs, and this is an easy question. All right, so the question description is very short. Given an array integer nums, a pair ij is called good if nums I equals numj and I is less than j. Return the number of good pairs. All right, so let's look at some examples. So here we have this array. There are 4 good pairs, 0, 3, which corresponds to this one and this one, right? That's a pair because 3 is bigger than 0 and nums 3 equals nums 0. They're both 1, right? Here's another pair, right? 0, 4, they're both 1. And 3, 4, which is these two, right? They're both 3. And finally 2, 5. Which is, 3, 4 is these two 1s here, right? So that's a pair. And then 2, 5 are these 3s. So that's another pair. So in total, we have 4 pairs. Okay, so here there are 6 pairs, right? So, you know, these two form a pair, and then, yeah, so, okay, so I think the problem description is very intuitive of what's happening here. We just have to think of a way to solve this now. So if you look at the input sizes, you know, it's not that big, right? So the num's length is at most 100. So you can probably brute force this problem. And, you know, like most easy problems on LeetCode, they can all be brute forced. So the brute force solution would be just, you know, for every position, right? For example, for this index, you look at all the previous indices, and if you find a number that's equal to it, then you increment the good pairs counter by 1. So that will be like an O(n) squared algorithm, right? Because you have to basically check every single pair. So yeah, we can implement that. But if you think about this problem, there is a much easier way, because you realize that, you know, if you're going to loop through the array from left to right anyways, then as you're going, you can keep track of the numbers you already saw, right? Because at each position, say we're on this position, the only numbers that we care about are, you know, that could potentially form a pair with this number here, are the numbers that occurred before it, right? So, you know, as we're getting here to this index, we can just keep track of all those numbers as we go along. So then once we get here, we can just, you know, retrieve how many numbers are equal to this number so far in like an O(1) time, right? Because we have already kept track of all that. So in that case, we can get an O(n) algorithm, okay? All right, so what we're going to do is we're going to create this dictionary. Just like we said, we're going to have to keep track of how many of each number that we encountered as we loop through this array from left to right. So we're going to keep track of this. I'm going to create a dictionary called freq, which is going to keep track of the frequency of the numbers that we already saw. And let me just make this area a little bit bigger. Okay. And I'm just going to make this an integer defaulted dictionary. So for those of you who don't know, in Python, when you make an integer defaulted dictionary, every single key is automatically assigned to the integer value 0 as the default value. And then from there, you can start incrementing or changing the value. Okay, so this is going to be very convenient for us because, you know, initially we haven't seen any numbers, right? So all the frequencies are going to be 0 anyways. So this is a good way to initialize it. And then we're just gonna, and also we need a pairs. This is gonna be the number of good pairs that we have. Okay, and then now we just loop through all the values in nums. So for n in nums, so first of all, we need to check how many n have we encountered so far up to this point? And how many there are, we're going to increment that number into the pairs variable, right? So pairs plus equals freq n, right? So for example, if we already saw this value of n 3 times before this, then this value of n can form 3 pairs, right? So that's why we increment the number of pairs by the frequency up to this point. And then finally, of course, we need to increment the frequency of n by 1, because now we have saw this number once again. And finally, we just return pairs. Okay, so this should work, so let's try it. Okay, so we get 4 here. Let's try this example. And we can also try this one. So we should get 6 and 0. Okay, so we get 6 and 0. All right, so are there any edge cases? Let's see. The length of nums is at least 1, right? So if nums has length 1, right? If there's only one number in this array, then there would be no pairs, because this loop will only go through once, and then for the first time we go through this loop, this frequency dictionary has all values of 0. So we don't increment anything here, and then at the end we just return 0, right? So that's good. And then yeah, so that's the edge case, and then all other situations num's length is greater than 1. This should work as expected. All right, so let's submit this and see. Okay, so there we go. We get a pass. All right, so on to the next question. The next question is called minimum average subarray 1. Okay, so let's start by reading the description. So given an array consisting of n integers, find the continuous subarray of given length k that has the maximum average value. And you need to output the maximum average value. Okay, so there's only one example here. Okay, so k equals 4. So we need to find a continuous subarray of length 4 that has the maximum average value. And in this case, this occurs at 12 minus 5 minus 650. So this subarray of length 4 has an average value of 12.75. And that's the value that we need to return. Okay. So, all right, so let's look at the constraint. So the array size can be up to 30,000. That's pretty big. So this is probably an ON algorithm, or n log n at the very most. And of course, k is always going to be less than or equal to n, right? Otherwise, it wouldn't make sense, right? Because you can't have a subarray of length k if k is greater than n. All right. So I think the first thing to realize here is that for a given array, there aren't that many subarrays of a fixed length, right? And we can just check every single subarray of length k. So for example, here, this is the first subarray of length 4, right? The next one is this one, and the next one is this one, and that's it. There are no more subarrays of length 4. So the number of subarrays of length k is like n minus k, basically. Or n minus k plus 1, I suppose, because in this case, there are 6 values, right? And k equals 4, and we have 3 subarrays of length 4. So yeah, n minus k plus 1. So it's on the order of ON. That's the point, right? So we can check every single subarray. So the idea here is that check every subarray of length k. And there are at most n of them. Okay. All right. So the only problem here is that, of course, for each of these subarrays, we need to compute the average, right? So the first thing that might come to mind, the brute force solution would be to just calculate, you just add up all the values in the subarray and then divide by k, and you get the average. But if we do this for every single subarray, if we recalculate this average for every single subarray, that's not going to be very efficient, right? That's going to turn this into an O(n) squared algorithm. So we have to find a way to calculate the average very efficiently. And the way that we can do that is, if we're going to check these subarrays, going from left to right, these subarrays can share a lot of values as we move, right? So for example, suppose we start with this subarray, okay? And fine, we sum up these four numbers when we calculate the average. But when we move on to the next one, right, which is here, this subarray of these four values and this first subarray shares two values, right? They share 12 and minus 5. So we don't have to recalculate the sum of those shared values. We only need to recalculate the sum of the values that changed, shifting from one subarray to the other. And if you think about it, only two values have changed, right? So if we start here and we move to the next subarray, what has happened, right? So first of all, we got rid of 1 by moving forwards, right? So we should subtract this value. But we gained a new value, namely we gained 50, right? So we should add that value. So therefore, once we calculate the average of the first subarray, as we move on to the next one, we can calculate the average of the subsequent ones in O(1) time, because we just need to subtract one value and add one value and just recalculate the average. Okay, so therefore, so I'm going to just loop through all this, try to implement this now. So I'm going to define this variable called s. So this is going to be the sum of the current subarray that I'm looking at. So first of all, I need to calculate the sum of the first subarray, right? So for I in range, and I'm going to, of course, only look at the first k values, and I'm going to add those values to s. Okay. And now, I should also define max average. So this is going to be our answer. All right, so after we do this, we set this max average to be s divided by k. But of course, in Python here, what we're trying to return is a float, right? We don't want integer division. So what I have to do is I'm actually going to have to convert this k into a float to force this division to be float division. So we get a float as the output. All right, and now we're going to have to loop through all the subarrays. Okay, so, and the question is, well, where do we start? So we already calculated the average of the first subarray, which is the first k elements, right? So therefore, if we move on, then we should start at the k plus 1th element, right? So in this case, we should start at the 5th element, which has the index of 5 minus 1, which is 4. So we should start at the kth element in this case. So for I in range, k all the way to the end. Okay, so now remember, what do we need to do when we move forward, right, with this subarray? We need to subtract this value that was at the beginning of the last subarray. So where is that, right? So that value would be at nums I minus k, right? Let's see, is that right? So in this case, so this here would have an index of 4. 4 minus k, 4 minus 4 will bring me to 0, which is this 1, which is the one that I want to subtract. Okay, that's good. And of course, we got to add on the new value, right? Which would be at the position I. Okay, so now, after we have done this, this s denotes the sum of the current subarray that we were looking at. And we just need to compute the average now and update the max average variable. So max average equals max of itself and the new average of the subarray. So s divided by float of k. Okay, and at the end, we just return this max average. All right, let's see if this works. Okay, so 12.75, and I guess that's the only example. I think in this case, sometimes if the logic of these problems get really complicated, there could be some edge cases where the indices don't quite work and so on and so forth. But I think in this problem, you know, once you figured out the solution, the logic is pretty clean, and you can be pretty confident that, if your code works on this one test case, you can be pretty confident that it should work in general. Okay, so let's consider, what happens when n is 1, right? So if n is 1, then k is going to be 1. In that case, okay, so then s will be just that, equal to the only element in the array, and this value would be just s, except in float. And for I in x range, k equals 1, 1 to length of nums is 1, so 1 to 1, so therefore this loop never enters, and at the end we just return max average. Okay, so in that case it would work as well. All right, so let's submit this and see what happens. Okay, there we go. We get a pass. All right, on to the next one. So the next one is, these problems are getting harder progressively. So the next one is a medium problem. And this one is called partition array into disjoint intervals. All right, so given an array A, partition it into two contiguous subarrays, left and right, so that every element in left is less than or equal to every element in right. Left and right are non-empty, and left has the smallest possible size. Return the length of the left after such a partitioning, and we're guaranteed that such a partitioning exists. All right, so let's see. So in this case, 503.86, output is 3 because the left is 503, right is 86, and all the elements in left is less than or equal to all the elements in right. Let's see, is it less than or equal to? Okay, it's less than or equal to. Okay. And that's the smallest value of smallest length of left that we can have. All right, so in this case, 1110, 612. Okay, so the partition is right here, down right here. And this is, okay, fair enough. Okay, so the problem description is very clear. And, if we look at the length of A, so length of A is at least 2, which makes sense, right? Because in that case, if the length of A is 1, we can't have a partition. So it's going to be at least 2, and it can be up to 30,000. So once again, this is a pretty big input size. So we're probably looking at like at an ON algorithm or something. All right. Okay, and it's guaranteed that there is at least one way to do this. Okay. So when it comes to these problems, it's always helpful to, first think about the brute force solution, right? And then try to optimize it on top of that. So what would be the brute force solution in this case? The brute force solution would be to just simply try every single partition, right? So we first, for example, partition here, right? 5 and then 0386. And for this partition, we check if every number, in left is less than or equal to every number in the right. And then we move on to the next one. We partition here, and then we partition here, and so on and so forth. We check every single partition. And for every partition, we check if this first condition here is satisfied. Now, if we don't do this in a clever way, this is clearly O(n) squared algorithm, because there are n possible places that we can do the partition. And for every single partition, if we loop through all the elements to do this checking of the first condition, that's another O(n) operation, right? So in total, it's going to be an O(n) squared. So O(n) squared algorithm on this input size is not gonna fly. We're gonna get time limit exceeded. So we have to think about some way of optimizing this. Okay, so I think there is no helping checking every single partition. I think that's kind of unavoidable. But can we optimize, or can we check whether this first condition here is satisfied very quickly, right? So that's the question. So let's see, every element in left is less than or equal to every element in right. All right, so how can we ensure that this is the case, right? Okay, so if we look at this array here, what is the maximum element here? This is going to be 5, right? The minimum element on right is a 6, and okay, so therefore, if we ensure that the maximum element in left is less than or equal to the minimum element in right, then we can ensure this first condition, right? So in other words, if we ensure that max of left is less than or equal to min of right, then we satisfy this first condition. Because if this were the case, then every element in left is obviously going to be less than or equal to this max of left, and every element in right is going to be greater than or equal to the min of right, right? So therefore, every element in left is going to be less than or equal to every element in right. So this is a much, this is an alternative way to check this first condition. And now the question is, with this alternative phrasing of this first condition, can we optimize it? And the answer is yes. So what we can do is we can just keep a prefix. Max and min array. So what this means is that I'm going to create these two arrays, left max, and this is going to have length A, and right min, and this is all going to have length A. And what these are going to keep track of is, so left max of I is the max of all the elements up to I in A. Okay, so A from 0 to the ith element inclusive. Okay, so I want to include the ith element. So this is going to be I plus 1 then in Python notation. And right min is min of all the elements to the right of I inclusive. Okay, so min of A from I all the way to the end. Okay, so that would be the length of A then. All right, so in this case, then the condition that when you check is left. Okay, so if we partition at I, and we're going to use the convention that ith element belongs to left. Okay, so this is going to be the convention that we're going to use. So if we partition at I, meaning that the ith element belongs to the left, then we check left max of I is less than or equal to right min of I plus 1. Right? This is what we have to check. And because we're looping this array A through left to right, as soon as this condition is satisfied, we need to return immediately, right? Because we need to find we need to make sure that left is as small as possible size. Okay, so now let's try to populate these two arrays, left max and right min. So for I in X range, range length A. Okay, so first of all, if I is 0, then we just do left max I equals just the number at A0. Otherwise, left max of I is going to be the max of the previous I minus 1 and this element A of I. Okay, and similarly, we do the same thing for the right min, except we loop backwards. X range for range length of A minus 1. Right, minus 1. If I, okay, so the first number we just have to set. So if I is length of A minus 1, right min of I is going to be A of I. Okay, to make it less confusing, I'm going to put A of I here as well. Right, else right min of I is going to be the min of the element after. So right min of I plus 1 and A of I. Okay, so by this point, these two arrays have been populated, and of course, these both are O(n) operations. We're doing one loop through A for each of these. All right, and now we just check this condition as we loop through. So for I in range, remember, we're using the convention that if we partition at I, the ith element belongs to left. Okay, so therefore, I'm only going to loop up to length of A minus 1. Okay, because I don't want to loop through, all the way to the end, for example, 6, right? I don't want to loop here because using my convention, if I looped here, there would be nothing on the right, in this right array, right? Because 6 by convention belongs to the left array. So that's why I stop 1 before, okay? And so in this case, we partition at I, and then we just check this condition, right? Namely this one. So if this return, okay, and then we got to return the length of the left array. Okay, so what is that? So let's see. What is that in terms of I, right? So I think that's going to be I plus 1. That's going to be the length of the left array. Yes, that is correct. And I think that's it, because we're always guaranteed, there exists such a partition. So in this loop, we always will return at some point. So therefore, this should be it. Okay, so let's run this and see if it works. Okay, so we get 3. That's as expected. Try this example. Okay, 4. This seems to work. Let's see. What about the edge case? If length of A is 2, then this stuff down here should still work. Then we still enter this loop because this number here will be 1. So therefore, we just enter this loop with I equal to 0. And we check this, and yes, that should be. And at this point, this is guaranteed to return because there exists a partition. So therefore, we just return 0 plus 1 is 1. So yes, that is correct. Okay, so let's submit this and see if this works. All right, so this did get accepted. Not a very good runtime though. But I mean, I think but nevertheless, this is an ON algorithm. There may be some ways to optimize this, but I mean, I'm looping through 3 times here, so this is like an O of 3n, but it's still O of n. Okay, so which I think for interview purposes is good enough. All right, on to the next problem. Another medium. So this one is called find 2 non-overlapping subarrays, each with target sum. All right, so given an array of integers, ARR, and an integer target, you have to find 2 non-overlapping subarrays, each with sum equal to target. There can be multiple answers, so you need to find an answer where the sum of the lengths of the 2 subarrays is minimum. Return the minimum sum of the lengths of the 2 required subarrays. Or return -1 if you cannot find such 2 subarrays. Okay. All right, let's look at some examples. So here, this is the array, target is 3. So only 2 subarrays can have sum 3, which is this one and this one. And the sum of length is 2, okay? 7. All right, so although we have 3 non-overlapping subarrays of sum 7, right? So we have 7, and then 3, 4, and then 7. We need to choose the first and third subarrays as the sum of length is 2, and that's the minimum. Okay, so we don't want this 3, 4 in the middle because that has a length 2. But rather we want the 2 singletons, 7, 7. That minimizes the length. All right. Here, target is 6. We only have one subarray of sum 6, so we can't find another one. So therefore, we turn -1. Okay, we can't find a subarray. Okay, so this is also -1. We can't do it. All right, so notice that the subarrays 1, 2, and 2, 1 cannot be an answer because they overlap. Right. So, right, so then here the optimal solution would be take this 3, and then let's say 1, 2 here, right? So then the sum will be 2, length 2 here, and length 1 here, so that'll be 3. Okay. All right, so this seems like a pretty complicated problem. We have a bunch of conditions. First of all, the subarrays cannot overlap, and they have the sum to target, and we also have to find the minimum length. Well, not just the minimum length, the minimum combined length. Okay, so what are the constraints? Okay, so size can be up to 10 to the 5. This is definitely requires an ON algorithm. All right. So let's see. First of all, always think about the brute force first, right? And then try to optimize. So what's the brute force solution? So the brute force solution would be, find. Okay, so let's say we're like here, right? If we're at this index, what we can do is we can find does there exist a subarray that ends on this index with the sum of target, right? That's the first thing we check. So for example, here, if we're at this index, does there exist a subarray that ends here with a sum of 3? And the answer is yes, namely this subarray, right? And once we have this subarray, okay, so the first question is this subarray going to be unique, right? If it exists. And the answer is going to be yes, because if you look at this constraint here, all the numbers in the array is going to be positive, right? So that means you cannot have two different subarrays that ends at the same place with the same sum, because there are no numbers in here that are 0, right? So if there exists a subarray that ends at some index with the sum target, then that is a unique subarray. All right, so, okay, fine. Sitting here, we found a subarray that ends on this index, right, with a sum of 3. And now the question is, can we find the other subarray with a sum of 3? Okay, so what we can do is we can just look before this and see if there's another one, right? So in this case, yes, there is, and that's this one, right? Or it could also be this one, but because we're looking to minimize, the sum of the lengths, we can't pick this one. We should pick this one, okay? And also, when we check for the second subarray, we can only check beyond 1 here, right? We can only check starting from this 5 and then going backwards, because the subarrays cannot overlap, right? Okay, so I think we have an idea of our general strategy. So what we're going to do is, for each index, check if exists subarray that ends on that index. Okay, so for each index, let's say I, ends on index I, that sum to target. And this is unique if it exists, right? Because we have because all the values in here are going to be positive. So if this does exist, it has to be unique. Okay, and then for this subarray, check for the smallest subarray that before it that doesn't overlap, that sums to target. Okay, so let's see. For every index, this step is obviously going to be an ON step, right? Because there are n indices we have to check. And then for each of these indices, we need to first check if there exists subarray that ends on the index I that sums the target. So we probably have to do this step very efficiently. We can't, just start looping backwards from I and try to add stuff up. That would be an O(n) squared process, which wouldn't work for this input size. So this step has to be done very, very efficiently. And then once we have done this step, we need to also check, for prior to this subarray, check for the smallest subarray. So this step here has to also be done very, very efficiently. Probably like O(n) or log(n) at most. Okay, so this step here, check if there exists subarray that ends on index I that sums the target. This can be done using a prefix sum, right? So that's fine. So this is a prefix sum, and this can be like O of 1, right? So that's fine. And then here, check for the smallest subarray before that doesn't overlap a sums the target. This calls, this step probably requires DP. Okay, so let's see. So first I need a prefix sum. So I'm going to define this prefix sum, and it's going to have length of array plus 1. So here, PS of I is sum of array from, let's see, up to I. So it doesn't include the ith element because there's yes. Yes, that is correct. There's just a one index shift between the indices of this prefix sum and array. And the reason I define it this way is because I want to make sure that when I do, the subtraction in this prefix sum, psj minus psi, I need to also include the case where like I include the prefix sum goes all the way to the beginning of the array, right? So it's just convenient to define, the first element of prefix sum as 0. So in that case, I also include that edge case. Okay, and then I also need a DP array. And this DP array is gonna length array plus 1. And this DP array is gonna keep track of the smallest length of subarray that ends on array of I minus 1. Yes, that's let's see. Yes, that's correct. That ends on I minus 1 with some target. And of course, that may or may not exist. So actually, I should initialize all of these to -1. So if I see a -1, that means I know that it doesn't exist. Okay. And now I'm going to populate the prefix sums. So for I, or actually I should start at 1, and then PS of I equals PS of I minus 1. So now you see why this is convenient, right? Because here I can, if I define this to have length of array plus 1, I can start at 1, and then I don't need to check the separate case where where I is 0. I can start at 1 instead, and I just do this plus array of I, or I minus 1, because there's a 1 index shift. And then I need to just do the DP. Okay, so let's see. Right, so I need something else here. I need to do this step efficiently as well. So I need to instantly know if I'm sitting at an index I, if there exists a subarray that ends on index I that's summed to target. And if it does, that has to be unique. So what I can do is I can create a dictionary of all the indices of the prefix sum values. So I'm gonna call this sum locations. And this is just gonna keep track of the index of all this of the prefix sum value. So for prefix sum and then sum locations, the prefix sum at I equals I. Okay, so this just allows me to retrieve certain values in all one time. All right, so now I can populate the DP. So I should start at 1. Okay. So the prefix sum at I, so this gives me the sum of all the elements up to the ith element. And I'm trying to look for a previous position that has that sums the target. So that means the previous position must have a sum. So what I want is a previous position j such that ps of I minus ps of j equals target, right? I'm looking for a j where this is satisfied. Or in other words, I'm looking for a ps of j such that ps of I minus target equals ps of j. Right? So what that means is that I can just check this in the sum locations dictionary. So if this value is in sum locations, then at this point I know exists a subarray that ends on I with that sum to target. Okay, so now I know this, so now I need to look for the other one. All right, so let's see. So in order to look for the other one, I have to look, so right, so I have to look, okay, so let me just get that j value first. So j is some locations of I know some locations of this thing. Okay, so this is the j value. So then I have to, for the second subarray, for the other one, I have to look before j, right, to ensure non-overlap, right? So, and what I can do is, so I need smallest subarray that sum to target that occurs before j, right? So that means I can just call this dp, right? dp of j. This is going to be the smallest one. Yes, so if dp of j is not equals to -1, then that means I know that the second one exists. So therefore, I can update my answer. Okay, so I need an answer variable. So answer equals, let's see, I'm looking for the minimum, so I should just start this at, for convenience, just infinity, and then I can just take mins. So min, answer equals min of itself, and dp of j, right? That's the length of the other one. And then also I need the length of this current one. So that's going to be I minus j, I believe. Yes. Okay. And then but I also need to update dp of I as well, right? So let's see, if I need to update dp of I. So initially, if dp of I minus 1 is not equal to minus 1, then I can just copy that value over temporarily. And then in this case, you know, if I find an array that ends on dp of ends on the ith position that has the target that has the sum equals target, then I can update that value again, right? So dpi equals min of dp of I and the length of this. So actually, I should do this after I get the value of j. J minus I. Okay. And finally, I return answer. Okay, so this is an example of one of those problems where the logic is like more complicated. So I don't have, you know, high confidence that this code will run completely error and bug free on the first try. But let's see what happens. If it does, then we'll debug it. Okay, so once again, not is in, right? Got to follow the syntax of the language. Okay, so obviously it didn't work infinity. So somehow I'm not entering this. Okay, let's see. Okay, I think I know what the problem is here. So in the event where dp of I minus 1 is -1, and then I go into here, then I don't want to do min of -1 in this. I just want j minus I by itself. So that means I should, so if dp of I is not -1, then I do this. But if it is, then I just want j minus I by itself. I. Okay. Let's see if that works. Still doesn't work. Okay, let's see. So let me just print dp to see what this looks like. So this is for, okay, so this is for this example. So this is definitely not right. So I'm not populating this DP array properly. So let me look at the prefix sum, see what that looks like. This should be correct. Okay, prefix sum looks right. So let's see. Then the logic here is somewhat wrong. So prefix sum I minus target in some locations. So right. So in this case, let's see. I'll print I and J to see what this looks like. 1054. Okay, that looks good. Oh, okay, that's stupid of me. J is the prior index, so therefore it's smaller. So therefore this should be I minus J, not J minus I. Yeah, okay, yeah, I got it right down here, but somehow like up here, I don't know, I flipped them. Okay, let's see. Okay, so that gives the right answer. Let's try a different one. 7. Oh, yes, I shouldn't just return answer, because if a pair doesn't exist, I return infinity, right? That's not right. So I should return -1 in that case. So return answer if answer is not equal to infinity. Otherwise, return -1. Okay. Let's try 6. This one. So this one should give -1. Okay, -1. And let's just try these two examples here. 3. All right, so this looks like it works. Let's try it. All right, so we get a pass. In terms of the time complexity, this is, of course, O(n), because up here, populating the prefix sum is, of course, O(n). This is another loop through the prefix sum, that's O(n). And here, with the dynamic programming, this is a single loop of length n. So this is just 3 O(n) operations, so therefore overall it's O(n). All right, that problem is done. Now on to the final problem, which is a hard problem. Distinct subsequences. Given two strings s and t, return the number of distinct subsequences of s which equals t. A string's subsequence is a new string formed from the original string by deleting some, okay, and it is guaranteed the answer fits into a 32-bit signed integer. All right. Okay, number of distinct subsequences of s which equals t. Okay, so we have t equals rabbit, and there are 3 ways you can generate rabbit from s. Okay, so you can take these characters, these ones, and these ones. Okay, fair enough. There are 5 ways you can generate bag from S. Okay. All right. So, okay, so the length of S and T can be up to 1000. So this is probably an n squared algorithm, which hints at dynamic programming. If we were to do dynamic programming on a prefix of S and prefix of T, right, then for every single state of those prefixes, there are, n squared combinations. So it's probably something like that. Okay, so let's think towards that direction, right? So if we do dynamic programming for this, how does it work? So let's imagine S is we have I don't know, some characters. Okay, so dynamic programming ij, and this is going to give, so this is going to be the answer for S to I, and or let's do inclusive, S to I plus 1 and T to J plus 1. Okay, so how does this work? So the question is, okay, so there are 2 possibilities, right? So on one hand, T can be at the end of S, or rather, yes. So this T to I, T to J plus 1 might be at the end of S, right? So this requires, in particular, T of J equals S of I, right? So this requires this. And then, if this were the case, then we just need to check dp of I minus 1, J minus 1, right? Because the idea here is that, let's say S was okay, so let's say S of I plus 1 was something like, A, B, C, D, E, right? Okay, something like this. And then let's say J of, T of to J plus 1 is something like, DE, right? So if the end characters match, in this case it's E, right? Then this T can potentially fit at the end of S, potentially, okay? So if they match, then all we need to check, we don't need to check this final character anymore because they match. We just need to check whether the rest of T, excluding this final character, how many times that matches in the rest of S, excluding this final character. So that's why we do check dp I minus 1, which excludes the last character of S, and then J minus 1, which excludes the last character of T, right? So in this case, the answer is just, let's see. It's just going to be equal to this, right? Equal to dp I minus 1, J minus 1. Well, actually, no, it's not just equal to this, because, yes, so T might fit at the end of S, but it also might fit before it, right? So we have to, maybe this DE appears before this final character of S. So we actually have to add on to this dp of I minus 1 and all of T, right, which is J. Okay. So on the other case is that, if these two are not equal, right? So if these two are not equal, then this T cannot possibly fit at the end of this S, right? Because the final characters don't match. So therefore, we just try to fit this T before this final character of s. So in this case, the answer is going to be dp of I minus 1 and all of t, right? Okay, so therefore, well, okay, so first of all, what's the base case? So if I is less than j, then there's no way we can fit t into s, right? Because if I is less than j, that means t has more characters than s. So in this case, we should return 0. Okay. So at this point, we must have I is greater than or equal to j if it hasn't returned. So that means the other base case is going to be if j is minus 1, then t is going to be empty, right? If t is empty, how many distinct subsequences of s is empty? That's 1, right? So we return 1. Okay, so those are the base cases. And now we just implement this the rest of this DP stuff. So, okay, so in these two situations, either way, the answer is going to contain this, right? DP I minus 1j. So we might as well just set that. And then if this condition holds, so if the last characters match, then we add on to this contribution, this additional contribution of I minus 1, j minus 1. And finally, return answer. Okay. So we just return dp of, so of course we want the answer for the whole thing of s and t, so we need to do length of s minus 1, length of t minus 1. Okay. This is of course not optimized because this is just, we're going to end up recomputing many of the values here, but I'm just going to run this on small test cases to see that it works. Okay, so that seems to work. Let's try another one. Okay, so this seems to work. Fine. So now, like I said, this is not optimized. So let me just get rid of all this stuff here. Okay, so now, like I said, this is not optimized because when we do this recursion in DP, we might end up computing the same ij pairs, the answer for the same ij pairs multiple times. And in that case, we wouldn't get a true n-squared algorithm because that's going to waste a lot of time complexity. So we're going to do we're going to memorize or store all of the values that we have computed so that, you know, if we do happen to have already computed it, we can just call it immediately from the memory. So so if this pair is in memo, or not is in memo, then we can just fetch that value, return memo of ij. Otherwise, if it's not, then we have to compute it, of course, by going through all of this stuff. And then at the end, we need to store it in memo. So memo ij equals answer. And return answer. Okay, so now what's the time complexity of this, right? So this DP takes in two arguments, I and j, and both I and j can be, you know, so I can be up to length of s, j can be up to length of t. So there are in total length of s times length of t DP possible DP states, right? And for every DP state, we're doing only O1 operations, right? So we're you know, checking like some if statements, we're checking an equality of the characters, and yeah, so these are all O1 operations. So therefore, in total, like this algorithm should be O and time complexity should be O of length of s times length of t. Okay. Just run this again to make sure that I haven't messed anything up by doing the memory. Okay, that looks fine. Let's run this to see what happens. All right. Wow, that's actually very fast, considering the lengths of these. So I guess they didn't give test cases that are too big. All right, so that's that. So I hope you guys have enjoyed this this session of LeetCode Challenge, and I hope you have learned something out of it. Whether it's how to approach problems, how to think about dynamic programming, and how to think about these array type problems, prefix sum, and so on and so forth. So I hope this has been educational. And yeah, if you have any questions, please leave a comment. And if you like this video, make sure to give this video a like and subscribe to our channel. And I'll see you guys next time.